I thought I had it all together, but I was led astray the day you walked away. You were the clock that was ticking in my heart. Changed my state of mind. Love's so hard to find. Your feelings changed like the weather. Went from clear to gray. All that time we paid.
Hey kids, what you just saw was a demonstration of the dentate gyrus going off. This is a part of the human brain which controls curiosity, and the one responsible for all the "do bald people use shampoo or soap?" or "do all dogs bark the same language?" kind of questions keeping you up at night. The gyrus is also responsible for the countless hours I lost as a kid trying to line up both north poles of two magnets, only for them to repel each other with some sort of invisible super beefy arms. While trying, one of the magnets actually slipped out of my hands. They were two of these Boss magnets which are super brittle, so it actually broke in half. Fast forward 10 years, and when told in college that cutting a magnet in half would not result in a separate north and south pole, but rather a new dipole magnet, my dentate gyrus started buzzing like some sort of nerdy spider sense, asking whether or not monopole magnets could exist. And upon a phone call with the big man upstairs, I am pleased to say that
to answer that, we need to talk about parallel universes.
By which I mean quantum physics. You might be familiar with this image. It shows the magnetic field lines of an ordinary dipole magnet. The same shape even applies for the Earth's magnetic field, to whom I'd like to thank for sponsoring this video by protecting us from being boiled alive by solar wind blasts. If you've ever heard the phrase opposites attract, you should know that it applies not only to magnets, but to electric charges as well. Here we see both a proton and an electron, which hold positive and negative charge respectively. You can also see each particle's electric field lines, which in contrast to the curved lines of a magnetic field, are perfectly straight. But when combined, they almost resemble those of a magnetic field. By the early 20th century, electricity and magnetism were already well known to be just two sides of the same coin. So well known, in fact, that you could already find careers in electrical engineering in some of the most well-renowned universities in both Europe and the US. You might already see where this is going. If electricity and magnetism are just different skins of the same guy, how come the shapes of their force fields behave so different? More so, how come we can have positive and negative charges studied separately as easily as stabbing a lemon with a bunch of nails, and still, monopole magnets are yet nowhere to be seen in nature? This question got into the nerves of many scientists of the time, but especially on these guys. These questions were the bald soap or shampoo enigmas inside Sir Paul Dirac's mind, and after a lifetime of hard work, I think we can all agree to say he nailed it. Without a doubt, what Dirac is most well known for is for the equation carrying his name, the Dirac equation, which is this bad guy over here. It might not look so intimidating as to have won a Nobel Prize in 1933, but it was actually his goal to reach a natural-looking, elegant equation. Reportedly, his conclusions not being mathematically beautiful enough was actually a sign for Dirac to conclude that he was backing the wrong horse. He strongly believed that the universe was structured in a satisfying, perfectly symmetrical way. So much, in fact, he might have coined the term religion of mathematical beauty. This very concept was what took him to later predict the existence of antimatter around 1928. In case your quantum lingo is a bit rusty, antimatter is a real thing, where each particle has a sort of evil doppelganger that whenever they meet, they can't help but annihilate each other, releasing a bit of energy in the process. Each particle has its own nemesis. Electrons hate positrons, protons antiprotons, neutrons antineutrons, weeaboos and showers. You get the picture. This idea led Dirac to conclude that if every particle and trait in the universe comes in pairs, monopole magnets should and must exist, as two twin concepts which together explain common dipole magnets. Antimatter was first observed in 1955 in Berkeley, California, and is now a common thing to analyze in CERN's Large Hadron Collider, the LHC. As to monopole magnets, we haven't been so lucky. CERN has been preparing and running experiments related to finding traces of momentary magnetic monopoles as byproducts of hadron collisions for at least 10 years. They haven't detected any yet, but the theory and the numbers have been checked and double-checked 1,000 times by 1,000 scientists, and it all appears to lead to the conclusion that monopole magnets, and therefore particles with magnetic charge, could have formed in conditions similar to those of the Big Bang. These experiments do cost European governments more than you could ever spend on a steam-buying frenzy, but CERN scientists work day and night in hopes that what now is just theoretical physics could soon help us find the key to the deepest mysteries in the entire universe, including the hygiene habits of hairless people. Thanks for watching.